What we're asked to do in this problem is look at a 3-segment rod made up of segments 1, 2, and 3. The properties there are shown there in the problem description. These 3 segments are joined together at these rigid connectors there at B and C. What we want to do is calculate, as a result of the applied force P to the right there in connector B and the same magnitude force applied to the left there at connector C, what are the axial stresses in elements 1, 2, and 3? And then what are the horizontal displacements at UB and UC? Well, one thing that we should do here is anticipate. I'll put this in parentheses. It doesn't help us get the answer, but we should anticipate that the problem is statically indeterminate. Why is that? Well, if we look at the rod as a whole, we just simply look at the forces acting out from the outside. There would be an axial force here at A, an axial force there at B. And from knowing that we only have one equation for that rod as a whole in the x direction, we would be looking at 2 unknowns for that single equation. So anticipate that. Know that that's going to influence the way that we solve the problem. What I'm going to do as my first step is one we always do, and that's draw FBDs. I'm going to be looking at FBDs of the individual segments of the rod. So for segment 1, I'm going to draw the forces as if the loads were in tension. I don't know that for a fact, but that's just going to be an assumption that I make, and I let the math in the end tell me if I'm right or wrong. So then the force on coupler B is equal and opposite there of F1. Then the load that's carried by member 2, that would be called F2. Newton's second law, or third law here, says that equal and opposite force on the connector there, B. Let's not forget that there is this applied force P acting on B. Moving over to connector C, an equal and opposite force there of F2. We look at the load carried by member 3, that's F3. And by Newton's third law, equal and opposite force acting on connector C. And then, of course, acting on C is the applied force there of P. So although we drew the free body diagrams of the segments themselves, what we're really just going to use are the FBDs of our connectors there at B and C. So if I look at connector B, if I sum forces in X, get minus P1, I'm sorry, that should be an F1, minus F1, plus F2, plus P, and for equilibrium that is a 0. That's my first equation. The second equation, equilibrium, I should maybe point that out, that these first equations are simply coming from equilibrium. If I sum the forces acting on connector C, what I have there is an F3 minus an F2 minus P equal to a 0. And this is our first real hard evidence that the problem is indeterminate, as we suspected. Because here, what we have 2 equations for equilibrium with 3 unknowns, and the 3 unknowns are F1, F2, and F3. Let's not worry about that yet, but just know that that is an issue here. We'll write down our elongation equations. For each segment, we can write down an elongation equation. For segment 1, we'll say the elongation E1 is F1 L1 divided by E1 A1. That's just the standard equation. L1 is 2L, as given in the problem, and the cross-sectional area is there. That's cross-sectional area of A. It's got a Young's modulus of E. So this becomes 2F1L divided by EA. Element 2. Elongation 2 is F2L2 divided by E2A2. Again, the standard equation. So this is F2. It has a length of L. It has a cross-sectional area of 2A. So that elongation equation becomes 1/2 of F2L divided by EA. And then for element 3, I write down the elongation equation, the standard one, that's F3L3 divided by E3A3. It has a length of L. It has a cross-sectional area of A, so this becomes F3L over EA. So these are our elongation equations. Now we talk about the displacement equation. And this is where our compatibility equations come. So for displacements, what I will say is that the displacement, the actual displacement of coupler B, is going to be just the elongation of element 1. The displacement of coupler C, that's going to be the elongation of 1, added to it the elongation of 2. And if we go over to the far right-hand side of the wall, the elongation here is E1 plus E2 plus E3. But one thing that we know is that this is actually equal to a 0 because at D is a wall. So this becomes our compatibility equation. The equation that relates together our elongations. So what I'm going to do is take my elongation equations. E1, we recall, was 2F1L over EA. I add to it E2. E2, the elongation equation, was 1/2 F2L divided by EA. And lastly, the elongation equation for element 3 was F3L divided by EA. So this is a combination of our elongation equations and our displacement equations. So I cancel out the EAs across the board, cancel out the L's. So this equation gives us 2F1 plus 1/2 F2 plus F3 is a 0. So this is going to be our equation 3. Recall that we knew the problem was statically indeterminate. We were able to get two equations from our coupler equilibrium, and this is our third equation to help solve for our 3 unknowns. The rest of it is just solving these 3 equations. So solve, what I did was took equation 1, and I solved for F2 is equal to F1 minus P. My equation 2 gives me that F3 is equal to F2 plus P. And so we'll substitute that in. This simply becomes F1. So F3 and F1 are the same. So this is equations 4 and 5, resulting from equation 1. Then I take equation 4, which I just found, 5, and 3. 3 being my compatibility equation. And I get 2F1 plus 1/2 of F1 minus P plus F1. So what you see, what I've done is I've reduced it down from 3 equations, the 3 unknowns, down to a single equation in terms of a single unknown. So from this, I see on the the left-hand side, that's a 7 halves F1. On the right-hand side, it's equal to P over 2. So from that, I get that the axial load F1 is equal to 7 times the load there, P. F2 is equal to P1 minus P. So that ends up being 6P. And again, F3 and F1 are the same, so that's 7P. So these are the loads, the forces. What we're asked to find are these stresses. So that these stresses are sigma 1 then is equal to F1 over A1. So that gives us 7P over A. The stress in segment 2 is F2 over A2. That will be 6P divided by 2A. So that ends up being 3P over A. And the stress carried in segment 3, that's F3 divided by cross-sectional area 3, so that gives us 7P over A. So these are the stresses that we had in segments 1, 2, and 3. Please note that these are all tensile. How do I know that? Well, I assume at the beginning all the members were in tension, and as a result of that, I got plus signs all the way through, which mean that my assumption was correct. So we can go back through and we can calculate the displacements there for B and C. That's really an afterthought here, but UB here is equal to E1. You can calculate that out using those elongation equations, and UC is equal to E1 plus E2. Again, once we know our axial loads there of F1, F2, and F3, we can calculate those elongations and get the displacements there at B and C. So again, this problem is statically indeterminate. Depending upon how you write down your equations and how you count your unknowns, we are one short. Either one equation with 2 unknowns overall, or looking at the couplers themselves, we get 2 equations and 3 unknowns. That's no problem because it's statically indeterminate only if we look at rigid rods. But we took into account the elongation, E1, E2, and E3. We wrote down those relationships, and the key one here actually was our compatibility equation, which said that even taking into account our elongations, the displacement there on the right-hand side must be a 0 because there's a wall, and that gave us our third equation from which we solved for F1, F2, and F3.